So the kinetics of dissolution is a branch of chemistry regarding the rate of dissolution of solid. In our investigation, we are going to imagine placing a sphere into some liquid. As the sphere dissolves, we know the particles will be dispersed, and the sphere will shrink inside. So let's just go over some important definitions. So dissolution rate is the amount of solid dissolving in solution per unit time. And the saturation concentration, or the solid solubility, is talking about the maximum quantity of solid that can dissolve in the liquid. Past this point, any extra solid that is added will be precipitated. The aim of my research is to try and develop a mathematical model for the dissolution rate of a sphere. So let's just have a look at why our research may be important. So I'm just going to quickly go over one article that shows some practical applications. Beta-2 adrenergic receptor agonist is a class of medication we use to treat asthma and COPD. This drug can cause relaxation of smooth muscles in the airways, which is what we want. However, it can unnecessarily increase the heart rate. So we want to model our drug so that its concentration is maximum in the airways, but upon reaching the heart, it actually reduced to a much lower safety level. Another possible application is drug absorption. So drug absorption refers to the movement of drug from the site of administration to the bloodstream. And the rate of drug absorption can influence many factors of the drug. This can be its effectiveness, safety, onset, the intensity, and the duration of action. So to be able to control drug absorption, we have to control its dissolution rate. So let's now have a look at the model that I've developed. My initial step in modeling was to firstly develop a formula for the changing surface area of a solid. This is because surface area is an important factor affecting dissolution rate. In the equation shown, X represents the solution concentration at some time. XF, as we see here, represents the final concentration, that is, after the entire solid has dissolved. The final concentration is the solid's mass relative to the liquid's volume. Now let's see how we can apply our favorite formula. We have what we call a noise-weight equation. This provides a relationship between the dissolution rate, which is dx on dt, and the area and the saturation concentration minus our concentration. So dx dt is directly proportional to area and saturation concentration. In other words, the dissolution rate will decrease as the concentration approaches the saturation concentration. The K value, we call that the rate coefficient, and it can depend on other factors of the chemical we're using. Now, what we can do is we can substitute our area expression that we have developed earlier into the noise-weight equation, and we get what is shown on the slide. Next, I'm going to introduce a new symbol Y, just to make our formula in a more convenient format. As a result, we now have a new expression in terms of Y, K, and R, where R is specifically the ratio of XS to XF. So here is a graphical representation where we plot the X on X as X versus the time KT for 3 arbitrary R values. For R equals 2 here, we can see that the graph plateaus, indicating the maximum concentration that occurs around this level. For R equals 0.1, which is what we see here, the graph does not seem to plateau, but the concentration increases to a much higher level, as we can see, before the graph starts to level off. For R equals 1, the graph is somewhere in between. So what interpretations can we make from this graph? So when R equals greater than 1, so recall that R is XS on XF. That's when XS is greater than XF. The final concentration is limited by the complete dissolution of the entire solid, because the concentration can no longer increase, obviously past once the entire solid is dissolved. For R equals less than 1, which is when XS is less than XF, the final saturated concentration is limited by the saturation concentration. So as we can see in the graph, it seems that the concentration kind of is asymptotic to the saturation concentration. We are also going to look at what the R value in our equation can represent in a real life scenario. So the smaller the value of R, so to decrease R, we could increase xf while xs remains constant in our expression for R equals xs on xf. This corresponds to using the largest steel to start, resulting in a higher maximum concentration. So to generalize, the lower the value of R, the larger the volume of the solid. In terms of changing xs, we can try to vary the temperature of the solution. We will discuss that in the later part of the presentation. So how can we determine what the R is in our equation? So we call it R is xs on xf again. So let's start with finding the saturation concentration. So to find xs, we can develop a formula for that by using a concept that the Gibbs free energy will be zero at the saturation. So the Gibbs free energy is the energy associated with the solution that is available to do work and determines whether or not the reaction will be spontaneous or not. So the Gibbs free energy is related to the enthalpy change and entropy change of the solution by the following equation. Delta G is delta H minus temperature times the entropy change. So we can substitute delta G is zero into this equation and subsequently do some mathematical manipulations to obtain a formula for xs, which is what we want. So a model was developed for calculating the saturation concentration as shown. It looks quite complicated. So the x on the left-hand side of this equation represents the saturation concentration, while the q represents some energy at some temperature. So how we can solve this equation is we can plot a graph of the left-hand side, and we can also plot the graph of the right-hand side. So we get what we see on the slide here. So the graph on the slide shows the left-hand side of the curve and the horizontal line y equals q. For y equals 0.4, we can see that there is no intersection, meaning we cannot actually determine xs. For y equals 0.36, the line y equals q intersects the curve at the maximum turning point. For y equals 0.3, we can see that the x value is approximately 0.15, as shown in the intersection. So how can we graphically interpret that? So we can see that the higher the temperature, the saturation concentration increases. And a possible theory to explain this is, with a higher temperature, the molecules have higher kinetic energy. So the particles are able to collide more frequently, resulting in a higher number of particles dissolving. However, there comes to a point where we cannot actually determine xs, as we saw there's no intersection on the graph between the horizontal line and the curve. A possible implication is that for extremely high temperatures, the entire solid can dissolve, but regardless of its initial site because of the high temperature. But this is only theory at the moment. Let's now go over some limitations of our model. So there's numerous models, obviously, that comes with a mathematical formula. But I'm just going to focus on the most important ones today. Firstly, this model is limited to speed, but in reality, medicine tablets can take many other forms. For example, medicine tablets can become more oval shaped, or there might be some cubic shaped medicine tablets as well. Furthermore, we assume that the sphere maintains its spherical shape throughout dissolution. In reality, as a solid dissolves, its morphology is not going to stay as a sphere. It might become more irregular as it dissolves, which can impact the dissolution rate. So to improve, we could consider developing models for other 3D shapes, such as a cube or prism. And we could also consider using multiple functions to model the morphology of the solid. And we could, so for example, a sphere may later turn into the shape of a cube. So we could use a piecewise function for a sphere initially, but then after some time we could change the formula to a formula for a cube, for example. So to conclude, we have been successful in developing mathematical formula, but these are generic and these need to be experimentally verified. And we have to test if they actually work for specific chemicals. Because specific chemicals may have different physical properties and particle interactions that this investigation did not consider. In particular, our model showed that XS cannot be determined for high temperatures. So we need to experimentally see if all the solid will dissolve at high temperatures. And that's, thank you.